Right, so let's do this stuff. Here's the SEH-based Stack Overflow exploit, and I'm going to show you this. I just updated this to Python 3 and all that, so it should be all set to go. So I'm just going to move the instructions to another pane so I can see them. Now, I wrote this for an Intel-based processor, so I'm using my private cloud here, since I'm on a Mac M1. I thought it might be fun to do this on a ARM-based processor too, but I haven't written that version of it yet. This is the Intel version. And we are going to write some Intel assembly code here, so I don't think these tools will work exactly right for ARM. So the ARM-based version of it will require some different techniques. So we're only going to do the Intel version tonight. So I start this machine up. Let's see if the console is ready. There we go. I got a Windows machine. Okay. Let me log in. There we are. I have a Windows machine, and I have a little problem opening a command prompt. I wonder if I can do this. Oh, good. Okay, I can use the keys. I can't see the bottom of the screen, but I don't have to there. I just want a command prompt so I can do ipconfig. All right, so there's the address, 192.168.11.24. Now I have a Linux machine, which is a cloudless Debian server. A headless Debian server here. So if I do IPA, whoops, not listening to me. It hung up on me, all right? Let me start it up again. Let me make sure I've got my VPN. I do. All right. Let me start the terminal here. It seems to hang up on me after a while. I tried to set it up before class, and it hung up on me, so it's here. SSH into my private cloud. All right, now I'm in. So now if I do IPA, it will show me the addresses I have there. And you see I have a 192.168.11.29. Now the Windows machine has got 11.24. So the first thing is I have to make sure I can reach it. Let's ping it. All right, and I can. You can't do this project without a Linux machine that can reach your Windows machine. So this is the attacker, that's the target. Now, as we did before, we're going to run this vuln server product. So it's in the downloads folder. So hit this. I should be able to open some kind of folder. I guess I'll just open this. No, it's not going to do it. Okay, got to have File Explorer. There we are, File Explorer. Okay, good. Learning how to operate without the taskbar. I'm getting there. All right, so I go to Downloads, and here's vuln server. It's unzipped, and just double-click it and run it. Okay, so now it's listening on port 9999, and so I can SSH into that address, or not SSH, but netcat on port 9999, and it tells me, welcome to vulnerable server. And if I help, I get responses, and if I exit, it exits. So this is good. We have the vulnerable servers working. Now, let me go into my 127 and ED319 folder here. Oops, got to have a capital D. All right, and I should have everything ready to go here. Oh, that's rude. Oh, I put it in the one above. Okay, let me fix this. Move ... flash SEH star to dot. All right. There's my exploit. So let's start with this one. All right, this is an exploit just like the ones we've done before. You connect to that server on port 9999, and then you send it some data. Now, I'm not bothering with the part we've done before where you do a denial of service exploit and you put in a non-repeating pattern to find the instruction pointer. I'm just telling you how far you have to go. This number, by the way, you have to adjust it based on your version of Windows by up to like 20. So the version I used on Windows 7 and Windows 2008 was a lower number. This is the number I need for Windows 10. So it puts in a bunch of A's. Then it's going to put in, that's the prefix. Then it's going to put in BCDE. And then enough X's to make a total of 4,000 bytes. So I know an attack with 4,000 bytes will cause the exploit I want, and you have to start with Gmon. Remember, when we're doing a simple buffer overflow, we attacked trun. This is another function on that server called gmon, and this is, you have to put in gmon and a few punctuation marks, and then the attack, and then carriage return line feed. So this will send an attack in, which has a BCDE, and hopefully this will hit the instruction pointer. So we need to run the vuln server in a debugger here, not just in a command prompt like this. So let's run the immunity debugger, and you'll see later it's better to run it as administrator for this project. We'll need that later on. The first part of the project, it would be fine to run it not as administrator, but later on you're going to need it as administrator. So I'm going to run the vuln server inside the debugger. So it loads it, but it's not running. And down there in the corner, let me make my window a little smaller so it gets on the visible part of the screen. There you see it's paused down there in the corner. There we are. That yellow paused tells you that the program is not running. I can't send any data to it. I have to run it. Now it's running. Now I can send my attack. And so my attack is SEH1. I send the attack, and see there was an error. Access violation when writing to 00C10000. So that is a flaw, but it's not writing something that I injected. So I didn't, well, for the buffer overflow, I managed to get an error that said it was executing like BCDE, data I sent. So this is not data I sent. I've caused a crash, but it's not clear where the data I sent is. The data I sent did not overwrite the instruction pointer, but it did overwrite the exception handler. And you can tell with view SEH chain. And in here, let me fix the font. There. You can see here, in the exception handler, here's AAAA, and here's the BCDE. So the first address in the handler has been overwritten by data under my control. So I don't control the instruction pointer, but I control the exception handler, and it did cause an exception, an access violation. Now the debugger has stopped to give me a chance to handle the exception. But if I run the program normally, it won't do that. It'll just go to the exception handler. So I can resume execution with Shift F9. That will pass the exception back into the exception handler, back into the debugger. And maybe I have to do Shift Function F9 here. Yes. And now it goes into the exception handler, and now I get access violation when executing 45, 44, 43, 42. So you see, I do control the instruction pointer. My attack causes an exception and overwrites the exception handler, and the exception handler goes to the code I put there. So I have gained control of the instruction pointer. The problem is I don't know what to put in there, and this operating system has address space layout randomization turned on. So I have to overcome that. So we leave this up there and go to my instructions, which are somewhere here. Okay. I'm going to close this stuff to get it out of the way. All right, here's my instructions. All right, so what we have to do now, let me, by the way, mention some things I skipped in the instructions. You're going to have to do this. Turn off DEP, Data Execution Prevention. So you have to go into Performance Options and turn that off. And you'll have to restart your server. And you have to turn off SE hop. I mentioned these defenses are going to stop us. So you have to go into Registry Edit and turn off this disable exception chain validation. You have to set it to 1. So you have to make these two changes, which I've already done on this machine. If you haven't made these changes, then the exploit will fail, and I put help boxes later to warn you if you hit those errors. So get your vulnerable server running, get rid of the firewall, and you'll find instructions here. I wrote these using Google Cloud Console, but if you're using local virtual machines, the process is very much the same. All right, so there's the DOS exploit that we just did. So now the next thing we have to do is you have to use Mona, which we've used before. Mona is a additional module you add to immunity, and you can use Mona to see what defenses are on the modules. So we did this SEH chain. All right, we're going to observe the exception handling. All right. All right, I don't need any of that. All right. So now, here's the strategy. Let me see if I can show you the stack pane here. Let's go back to Windows, and I'm going to do debug restart. All right, and move this, maximize it. I guess that'll do. That'll do. All right, now run it again. Then I'm going to send the attack again. All right, which is here. Let me get that junk out of the way. All right. All right. So now I've got the access violation. Now, notice, here's the stack. BFF1E8 is down there. If I view the exception handler, there, let me make this window smaller. Okay. And okay. There. BFFFCC. I sort of thought I'd see it. Let's try stepping into it with Shift function F7. Make one step in. Yes, there it is. After I step in from the exception, now this BFFFCC, see the third value on the stack matches where the exception handler is. This is what we're doing tonight. This is the point of it. This location of the exception handler is going to be different all the time. And I can't predict it, but it's on the stack. The third word on the stack points up here to data I control. So first I'm going to have to do pop return to go here. Then I'm going to go to this address I have to put in. So that's that's how it goes. All right. Now, let me go back to my instructions. All right. So now we're going to do mono modules. We need to find a module with a pop return that doesn't move around. So we've added Mona to this program, and so I can do bang Mona modules down here, and that will show me the modules. Here they are, various modules, and I wonder if I can make this scroll horizontally. I'm not having any luck. Let me see if I can highlight it with Control A. Nope. All right, I'm going to drag through it. Nope, won't let me drag through it either. Command A. All right, this is pretty annoying. All right, anyway, I'll go to my instructions then where I have a picture of it that's the right size because I don't know how to shrink that font without fouling everything up. So here's what you have is a variety of modules, and it tells you whether they have safe SEH turned on or ASLR or non-executable for that memory there. And here's the various modules. So you see vuln server is old legacy code with all the defenses turned off, and ESS-func.dil came with vuln server and it has all the code turned off, all the defenses turned off. So all the rest have a lot of these defenses turned on, so I'm not going to be able to find an address there. So I can use these two options. The problem is vuln server is of course loaded at 400,000, where code is always loaded, and that therefore all those addresses start with 00, and the null byte will end my injection because it terminates a string. ASLMAR is address space layout randomization that chooses a random memory location every time you launch a program. Anyway, so the other thing is what I have to use, ESSfunc.dil. That loads at 6250.0000, so the addresses in there often do not contain zeros. So this is the same thing we did before. We have to use the ESSfunc module. So we're going to have to do this command, monorop, and we're going to have to find the logs. This is why you had to be the administrator. By default, this program does not have the ability to write the logs. So let's do options. All right, let me find out where it is. Edit options or something. Options appearance, okay. And then general, somewhere in this directories. Here we are, there. This is where it's going to put the logs. C program files x86, immunity inked, immunity debugger. And that's a place only the administrator can write. So that's where we're going to find the logs that we're about to create. So we execute this Mona command, bang Mona. It's bang Mona ROP minus M. Okay, so listening to me? It's not listening to me. All right, let me try and get back to the CPU window. View, CPU, okay. Now maximize this window. There, now I can get to this bar and put in bang Mona. Nope, still won't let me do it. I think because I have to get lower. I have to get this thing to move. Come on, stop messing with me. There we, no, there it is, bang Mona. Okay, there it is, bang Mona. Okay. I got to get to my instructions again. Bang Mona ROP minus M. Okay. And every time I get the instructions, this garbage pops up, but you can't have everything. Bang Mona ROP minus M ESS func.dil. That's what I need. Essential functions.dil minus M find return-oriented program. If I got that spelled right, it's too blurry in this projector to see, but it worked. I did execute the command. Okay, it's done, and it prepared the output file, and it put it in that directory. So I have to go to that directory, which is File Explorer will do. It was C, program files x86, immunity. Okay, and in here, you're going to find ropchains.txt. And I think the one we want is stack pivot. Let me check my instructions again. Yep, you want stack pivot. Okay. So you go to stack pivot. And there we go. So here is module information, the same information we saw before. Here are possible stack pivots. And there. And there's pop return, pop return. Here's some of them in ESS func. So you see there are various locations where the pattern pop return appears. So any of these will do. So you might as well just use the first one. The first one is fine. It does not contain a 0. 6250 10B4 is a location that contains this code that will not move. And I see a question, what is it good for? ASLR? ASLR, every time you launch a program, it puts it in a random place in memory, and the purpose is to stop these kind of attacks we're doing. So that if an attacker injects an address, they cannot figure out what address to put in, because every time the program relaunches, the address changes. So we have to use an indirect technique like this, pop return, to find the code we've injected. However, this is not randomized, so we can inject that address directly in our code. So I should be able to see this here. Now if I cat the SEH2, okay, here it is, 6250 10B4. That's the pivot address, put in here backwards. So now I got a prefix, then I have, I'm putting in a fake shell like we've done before. I only have 4 bytes to play with. This is what's pretty rude about it. This is my address. It's going to do pop return. It's going to go back here, but I only have 4 bytes of code to write before I'm going to hit the injection. So that's pretty irritating and limiting. But I did make a sample shell code here, nop break. So if this works, it will overwrite the buffer, cause an exception. The exception will go to my exception handler, which will go to the pivot, which will bounce back into the exception handler and an address under my control, and I can run this tiny little fake shell code of nop break. Why not?
You have the shell space only 4 bytes?
Because I can't control where it goes. It goes to the start of the exception handler. And so that's the best I can do. Just like if I had jump ESP, it would go to the top of the stack. And it's the way it's laid out. So if now someone asked a question, why not make a signature? And I do not know what that means. I need more information. All right. All right, let's go to View CPU and debug restart. And yes, and run. Okay, so the program is now running, waiting for an attack. And so if I run this one, SEH2, it triggers an exception, access violation. Now, I think I'll just do Shift F9 and run it. Maybe I'm going to do it step by step. I'm going to do Shift F7. You see how it goes. Okay, I've done Shift F7. So now it's gone to here. And I can now do F7 to step through this. F7. Okay, I'm stepping through it. So it's having whatever caused the flaw. And now, access violation when reading. Shift F7 again, I think. I'm not going to be able to do anything with my F7. There's the int3. Okay, I made it to the int3 command at this location. So if I roll back up, there they are. There's my nop. So I wanted to show you the whole process. I'm not sure I'm going to be able to do it, but I made it through my nop sled and ran it. Let me see if I can do that again. I'd like to step through the whole thing. I should be able to see it go to that 6250 address and come back. So let's do debug restart. Yes. Run. And now send the attack. And now it hits the access violation. So now we're looking at the instruction pointer here. And let's view the SEH handler, which is here. So there's the SEH handler pointing to 6250-10B4 at CCSFCC. And here's the beginning of, here's my NOP sled right after that, 9090.cc. That's all I have. All right, so now let's go back to the CPU, and let me see if I can step through it and we can see some of those addresses go by. Shift F7 will take one step. All right, and now it goes to CCFFD0, which is here. And here's the CCFFCC, third point on the stack. So now, oh, that's right. This is the 6250-10B4. I remember this. The debugger doesn't know that this is not assembly code, but it is the address. So now it's going to execute this as an address. It's going to put that in the EIP. So if I do one more step with F7, it's not apparently listening to me. Oh, no, okay. It went on to the int3 command. Okay, so somehow I wasn't able to control it. Anyway, it did bounce off it. I wasn't able to catch it in the debugger. I think that's because my debugger was not able to debug inside the DIL to come back. Anyway, so it did run the code, nop int3. If I had if I had SE hop turned on, it would have stopped when I processed the exception. It would have refused to process the exception because it noticed that the exception handler is corrupted. And if I had DEP, data execution prevention, turned on, it would have stopped on the NOP and said this is a non-executable memory. But I was able to execute code placed in this location and run my fake shell code. So now I have the ability to control the instruction pointer, and I have the ability to execute code I stick in. The only problem is I only have 4 bytes here. So let me go back to my instructions, and we'll talk about how to handle this. So, all right, we've done all that. All right, so now we had 3 NOPs and an A. Now before the 3 NOPs and an A is a bunch of A's. So, and then comes this address we put in, and then a bunch of X's. That's the structure of it. So we have to plan the attack. And, all right. And we could talk about where to put shellcode. Now you could try to put it after the SEH bytes, where the X's are. Or you could inject an address when you pop return in the SEH, and that would work. So we could put the jump plus 8 here to jump forward 8 bytes. This would be one way to do it. The problem is you can see in the debugger why this is not going to work. If you look at the code in this area, here's my current shell code. If I right click, follow in dump selection, notice here is my data. This is the stuff I injected, a bunch of A's. This is the 6250 address and then X's. But notice I hit the end of the segment very soon. I only have about 50 bytes before I hit the end of the segment. So I don't have enough room here to put shellcode. It takes about 300 bytes for normal shellcode. So I can't put the shellcode down here. The only place I can put it is way up here. But the problem is, I'm jumping into this area where I only have 4 bytes before I'm going to hit the 6250 I put in there. So I have to put something here that will jump back up here. Now, I have a problem with the instruction set of the 32-bit processor. If I go to my instructions, it turns out that to jump backwards, there, let me go back here. All right, you look at what code is available. You can jump with an 8-bit jump. You're only going to be able to jump 256 bytes, and that's only 2 bytes. If you want to jump back further, you're going to have 5 bytes, jump a relative 32. So the first 3 are relative jumps. That's what we need here. The rel 16 is only available when it's processing 16-bit mode. We don't have that. So the only thing we can use is the jump rel 8 and the jump 32, but the jump 32 is 5 bytes long. It needs 4 bytes for the address and 1 more for the jump. So the only instruction we can fit in the room we have available is a jump relative 8, and that can only move a maximum of 128 bytes. Yes, SE hop, I see another question here. SE hop is the security feature that checks the exception handler to make sure it is intact. SEH is the exception handler, and SE hop is the defense that's turned on servers, unless you turn it off. Exactly. All right, so this is the plan. We're going to have to use a relative jump to jump back a little bit, and then a second jump to jump back further, because we need to jump back 300 bytes, and we can only jump back about 128 bytes. So let me bring up my shellcode here. I can just cat SEH3. All right, here's how it works. This is what it is. It's nop break. This is the jump back relative, some small number, like 100 bytes. This is the jump 8. This is going to jump back 8 bytes, F6 EB, and this is going to jump back 450 bytes. I figured these out. And you can see this is the number -8, F6, I think. Yeah, this is the command. F6 is -8, because it's actually -10, because there's 16, and I have to have 4 for this instruction. So going back 10 bytes from this location, anyway, somehow this will take me back 8 bytes. I'm not quite sure how to figure it out. And this number here is a smaller negative number, FE3E. This is -450. So I can jump back a few bytes and hit this one, which will jump back further. And now I'm way back 450 bytes earlier, which is deep in the earlier bytes. So I can put in my shellcode. So this is my template of shellcode. I'm going to have a prefix, which is a bunch of A's. Then I'm going to have a jump, a pivot. So here's what I have. I have the prefix, the buffer, which is 500 breaks. That's what I'm using as my dummy shellcode. Then the jump 450, the jump 8, the pivot, and the post. That's the structure of this attack. So let's watch it go. I go back to here, debug, restart, and yes, and run. And now I send the SEH3. All right, and it causes an exception again. So if I do, I put in breaks in the exploit so we can easily see it go. So if I do a Shift F9, there's the F9. Okay, it goes and hits a break, and I can roll back here to see what's going on. All right, so it did the NOP and the break. Now it's ready to do the jump short, and the jump short is going to go to BEFFC6, which is here. So this is going to jump back just a few bytes to get here, but that's enough bytes to fit in this address, which is going to jump back further. So I do Shift F9, or just F9 now. And I have to click there to get in there, then F9. And that's, F7? Somehow, oh, I have to hit function, that's why. Function F9. There we go. Now it proceeds and gets back to here. So it jumped back up here to one of these NOPs and made it down to this interrupt. Now it's ready to do this jump. Now I'm going to do an F7 to follow that jump. That jump jumps way back 450, and that hits some of my CCs back here. So I'm hitting somewhere in my shellcode. So that's the plan, and it'll break again. So my basic template is working. The only thing missing now, of course, is I need real shellcode, and that we're going to get from Metasploit as usual. So after you got it working, and see how it goes, you're now able to jump back into a 500 long block of breaks. So now you just generate with MSF Venom, you can generate some code. This is going to listen on port 4444. No, I guess it's going to make a reverse shell. Okay, so I'm going to connect to my other host. So I have to generate shellcode using the IP address of my attacker. And it turns out there's some bad bytes to skip. Null, carriage return, and line feed, which are all reasonable back. You have to skip those bad bytes. You get some code, and you add that code to your exploit. So that's going to be my SEH4. All right, so here's what it looks like. Up here, I just define my socket to get to the server. Then I get the buffer that came from MSF Venom. And now I have a NOP sled, which is whatever it takes to make the total length 500. And I've added a break at the end so I can see it in the debugger. And here I have the same stuff as before, where it's going to have a couple breaks here. It's going to do the short jump, but break before it does. Do the long jump, breaking before it does. And then get ready to run the Metasploit attack, but break before it does. So this is only going to work in the debugger, where I can keep going through these breaks. But I did it that way so we can see it go. So let's get it ready to go. We go back to here and do debug restart. And run it so it's ready. And now we give it SEH4. So that causes the first exception. Now I give it a Shift F9 to continue through the exception. And that makes it to a break, which is here. So I made it to the start of my code where I have the short jump. So now I give it another F9. And it goes to the next int. This is the long jump. So I give it another F9. And now the long jump takes me back here, where it does all the NOPs, and then there's an int, and this is the actual code from MSF Venom. So I give it another F9, and now it's running. And since it's running, I've now opened my shell, and I forgot to start my handler. So I didn't get the shell, which I should have gotten, but I'll show you in the instructions. I don't think it's worth bothering to demonstrate it live. That's the point. Now, before you run it, you have to open a handler at the other end. So maybe I should do it just for completeness. So here's the handler. So I can go to my Linux box here. Okay, so I do. I don't need the sudo for this. You need it on the Debian Cloud machine, but I don't know it here. Don't need it here. So that's going to launch, and here's the code that will just make a handler. Okay, there. All right. So now I'm going to run my attack again. I'm going to need a second shell to my Linux box. All right. I'm going to need to go into 127 and ED319. All right. So this is ready to send the other attack. And here's my exploit. So I do debug restart. Run. Okay, now I send my attack, which is SEH4. All right, and now I'm going to move this over so we can sort of see it. It's listening. It hasn't got an answer yet, but it's going to get an answer. So now we've hit we've hit the exception. We have to do Shift F9 to send it back through the exception. And now I hit one of the int3s, so I need to do F9. And the next, this is the int3 for before the long jump. This is the int3 before the Metasploit shellcode. And if I hit F9 one more time, now it's going to run and see now it's sending data back to the server. So it's phoning home, sending back to the server, and now I have a shell on my Windows machine. So sysinfo, is that it? Yeah, I'm controlling my Windows 10 from here. So you see it works. Those breaks mean you can only do it in the debugger right now, but if you take those out, it'll run out of the debugger. And those are the steps to overcome it, even though it has address space layout randomization turned on. There are some other defenses we turned off, like SEHOP and data execution prevention. So, you know, again, this attack is not perfect by any means, but we have overcome some of the Windows defenses. There. And that's what I wanted to show you. So I'm going to stop this recording.